C, right, Control V. There we are. Alright, so what do we need from here? From here we need photovoltaic power. Also, let's run this and see how does this output look like. The other thing we don't need. Can go away and then save, and save. Go away. And let's see. Oh, it's still compiled. Okay. Alright. So okay, we see here that the power is reducing from 14 kilowatts, 14.2 kilowatts, it slowly decreases because it is past the solar noon. Actually, let me see if I can delete and Control C here and go away. Alright, I want to do actually 4,000 and go to 12 in the middle of the day where it should be. We could see also the ham. Let's see. I hope it's not a bunch of. Oh, that was fast. Which means I might be able to run more of this. And it's still climbing, so let's do it 13, and let's do this 8,000, which is more than 2 hours. Let's see, yeah, there we are. So now you see what is happening. So typically throughout the day, so if this is the 0 hour at midnight, this is the 24 hour of the next day, somewhere here is the solar noon, and it can be also at certain times of the year the actual hourly noon, and somewhere here we have 6 a.m., somewhere here we have 6 p.m. So let's assume that between 7 a.m. and 5 p.m. we have this behavior. So what we're seeing here is the photovoltaic power between, as I said, a little bit after noon zenith, and let's see. Yes, I started at hour 1 p.m. So maybe I'm somewhere here, and I'm seeing this part in this graph.
Professor, you put
Yes.
8,000. What does the 8,000 mean?
Come again?
You put 8,000, right? The stop time?
8,000 seconds.
Oh, 8,000.
So it's
okay.
about
Okay. Yes,
2 hours and change, because every hour is 3,600 seconds. So this is a 2-hour modeling
Okay.
of how roughly a photovoltaic behaves.
What time
Okay?
to what time? It's what time to what time? It's also depend on what time to what time, right?
This is seconds.
No, no, I know,
The
but
8,000, the stop time is in seconds.
oh,
So every hour has 3,600 seconds. So 1 hour is 3,600 seconds. So
No.
when I'm running this simulation for 8,000 seconds, 2 hours is 7,200 seconds. So I'm practically running this simulation for 2 hours and some minutes.
It started at 1 o'clock.
oh yeah, exactly. That's the question. I said.
That
It's
question, I'm sorry, I didn't realize.
like a starting
So-
time, yeah.
Yes, I'm starting at 1 p.m.
Oh, okay.
1 p.m. Okay, so
Okay,
that's why I'm
I
telling
see.
you, compared to the noon that is here, I'm
It's
starting
thicker.
my simulation somewhere around 1 p.m. And at 1 p.m., what I'm seeing is that my photovoltaic reaches its zenith, its peak power of the day, and then it starts dropping, okay?
Okay.
Alright, so what I want to do now is, let's put here the perturb and observe, okay? Let's remove that here. 2 kilowatts for 300 VPV, it means for 17 kilowatts it should be about 2100 PV voltage. So let's see what's happening here, and let's see how this system will look like. It will take a while, as you can see, but most probably it will get faster and faster. Let's see how this looks like. Open it. There we are. Okay, let's see what's happening here. All right, now you see how the voltage is getting adjusted in real time. Okay? I'm going to pause the simulation for some reason. I'm going to explain to you what's happening here. Okay, paused. Did it pause? Oh no, I'm not sure.
Yeah, it's both.
Okay, alright. So let's see what we're seeing here. I'm going to explain to you what we're seeing here. Every photovoltaic module, let me go and do exactly that. Alright, Control T. Go. Alright, let's see. PV module datasheet. Let's see a datasheet. Okay, so I'm going to show you how a datasheet of a PV model looks like. All right. Didn't have to click this one, but anyway, let's just click this one. All right. So this is one module. Okay, it has several cells connected in series, and you're going to see here in its characteristics it says let's assume that we're using a 420 watt module. A 420 watt module has an operating voltage of about 45 volts. So when I'm using one module, I'm expecting this module, this is the symbol of the module typically when you're doing its one-line diagram, it has 420 watt peak maximum output at an operating voltage of about 45 volts. So when I want to generate 17 kilowatts, I need to put in series several of these. How many? Let me pull out to see how many about modules we need to put in series. Alright, so it's going to be, calculate, come on, calculator. Alright, 17,000 divided by 420. 20, not 30. 40 modules in series. So I'm going to connect next to it another 420 watts 45 modules, another, all the way until I have connected in series. How many did I say? 40. 40. So 40 of them is going to have a total power of 40 modules, I said, is going to have a total power of about 17 kilowatts peak, and because I'm connecting them in series and they behave like DC sources, they're going to have a voltage of 40 times 45. 2 times 45 is 90, 4 times 45 is 180. So 180, so 1800 volts. So, I told you about right, that the voltage should be about 2100, okay? So, the one module, look at me closely here, the one module is going to have its peak of 420 watts peak at 45 volts. Again, this is at the maximum solar irradiation. So this is solar irradiation of 1 kilowatt per square meter. So the maximum solar irradiation. So for maximum solar irradiation, the maximum output of one module is 420 watts at 45 volts. When I'm connecting them in series, what happens is that I'm essentially compiling these curves and multiplying them. So for the whole string of 40 modules, I'm going to have 17 kilowatt peak power, PPV, at an operating voltage of 40 times 45, about 1800 volts.
Professor, what is the size of each module?
I just showed you 420
The size.
420 watt peak each module and operating voltage of each module of 45 volts.
Okay, that's the size.
That's one module. That's
Okay.
literally what you see here. That's one module.
Okay, the
so
whole
if you
thing,
put
okay.
one module under 1 kilowatt per square meter of sun, it should give you 420 watts if you make its voltage 45 volts.
Okay.
What does that mean, what I'm just saying? If I make the voltage at the terminals of this module 40, it will generate more or less power.
More.
Look at this. Less, it's going
Okay,
less.
40, yes.
Same thing if I make the voltage at the terminals of this module 60 volts. 60 volts. If I make the terminal voltage of this module 60 volts, I'm not going to get the maximum of 420, I'm going to get definitely less. So, the perturbed observed does what? It tries to find the voltage that I need to impose on the terminals of either one module or a string of modules in order to get the maximum output power. So that's why when I pause this simulation here, at the first few hundred seconds, the voltage, let me do something, it is not too difficult to fix this. So, let me do this one. Okay. Alright, centered, now better centered now. A little more. Seconds of the operation of the perturb and observe that takes in the input of the photovoltaic module, it starts to impose a slowly increasing voltage so as to cause the corresponding increase of the output power until the power becomes what the perturb and observe wants. So the perturb and observe is going to keep increasing the voltage reference that is imposed at the terminals of the string of the panels, of the string of these photovoltaic modules, until it becomes 1800 or so. And then it should stop and go the other way. Let's see if this is going to be happening. We are at the V reference is going to high. Why is it going to high? Because I don't have a watt. Because I need a return loop. Let me see. Yes, so remove that from here. Let me see something. Going here. Okay, string PM, seasonal adjustment, hour, seasonal adjustment, string power, PS. So the string PM, let's go up here, it needs to be occurring, not inputted. Go away. I cannot do it because I have paused the simulation. Okay. Let's do this. Okay, go away. So let's see. Okay, string PM, PPV. So this is going to give the output. Perfect. So if I keep it 17 kilo, because it is a multiplication, yes, I got it now. So Control Z. Alright, so what I'm getting out of here is that I need to VP. These two are giving me the current. Yes, yes. Alright, so I'm going here, and this becomes input. Come here, we go away, and what I need is to yes, the V reference is going to be increasing, and let's see. So as I said, we're getting the output here, which is the actual output, and here I have an imposing voltage. I have an imposing voltage. So the imposing voltage. Yes. Let's also make it according to the model with the 1800. Okay, so what I'm going to do here is that 1800, alright, divided, let me find no dividers here, I'm going to find one. I think there is one here maybe. Yes, Control C, Control V, okay, rotate, okay, and so 1800, alright, and now another one, and you see what I'm doing here. Multiplication, down here, actually to the, because I need to take this out and bring it here. Yes, right. Okay. So what I'm doing here, in case you're wondering, is that I'm trying to model the effect of the voltage to the behavior of the PV string. Okay. Yes. Alright. So this is going to be taking PPV, what do I need here? Here I need the VPV, okay. Can I make this loop, or it's going to be a closed loop? It might be a closed loop, and it's going to give an error. Why not try and fix it later? 1800, the reference, we also want to see the output here, the PPS, alright. Let's see if this will compile or not. I might need to add a small delay. Oh, okay. Alright. Oh wow, that was fast. Surprising. Let's see. No, it's an error. Of course there's an error. Like, yeah. Why did it go through the compilation? So this is 0, okay. So what I'm going to do is that I'm going to put a switch here from 500 to input. Let's go fixed point, and let's go Signal routing. Signal routing. No, signal routing. Yeah, signal routing. Where is the trigger? Where is the trigger? Where's the trigger? Index vector minus switch. Where is the switch that gets it? Ah, there we are. That's what I wanted. Okay, good. Okay, I'm going to put a step also. Sources. Yeah, take your sweet time. Why don't? Why don't you? All right, and let's put a step. There's a step. Okay. Thank you. Let's start it at 5. That's enough. And I'm going to use this here. What's the condition? Criteria for passing first input. Criteria for passing first input. Okay, that's the criteria for passing first input. Okay. And otherwise, let's have this little initial value here to play around. Let's make this 50. Alright, let's work on it now. Okay. Oh, yes, why connect it? I was silly. And so let's do this here. What am I doing? Yes. Delete this and connect this here. Now we're talking. So you're never going to be 0. Oh, why am I doing live so? There's another bright loop to here. Let's add a small delay. Transfer function continues. Come on. Let's add a small transfer function that acts as a delay to make our lives easier. Okay, and now let's move on. Let's start to the right. Thank you. Go away. Come here and come here. Let's see if the loop went away. Okay, there we are. Why? Alright. Okay, let's see if it's going to pass the 5th second. Nope. Does it need loops in both of them? Oh, I put the wrong part. Just realized it needs to be out. Yes. Alright, and here we are. And now it's not necessary here. Looks very ugly now, but anyway. Oh! I hope it didn't break the loop, not break the loop. It's running, it's past the 5th second, perfect. Let's see how is the power looking like. Okay. The voltage is slowly increasing. Okay. What's the time here? Let's see. 30 seconds, it's gonna run faster in a bit. I forgot to check if it is the older 23T. Is it? Can I see it? No, it's older 45. So let's change that because it's going to run slow and also cannot see much. Okay, now it looks better. Okay, so let's change the simulation to older 23T so it's faster. Thank you very much. And. Alright, RB23T, trapezoidal, okay, alright, and running it. Slow. Time is going to progress now. It should run much faster now. Okay, go past the 50 second. Come on, again. Doesn't go super fast, but it is going. Again, I have made several patches here to make the solution faster, but I'm going to explain what's happening once we get past some time. There's an accelerator also, but the accelerator might usually work opposite than what you want.
What do you mean?
There are accelerator options in the model parameters that, however, are not really accelerating the simulation. On the contrary, they're making it slower. Why is it going in the negative direction? I did something wrong clearly. Let's see what's the power. Oh yes, something is wrong here. Stop it. Okay, let's see what we're doing to clarify the problem. So let me tell you what I'm trying to do so we can work on it together. And so this thing, for this thing, I want to practically implement this behavior. Okay, so whatever happens with the voltage, this should give me the respective amount of power. So when I'm inputting this power here, this voltage reference should be adjusting the output power. For some reason it is negative, which makes no sense at all, because, let's see here, so this value should always be positive, like this is when the sun comes up, and I don't think I've done, no, starting out is 13, okay, starting out is 13, alright, what is this? Yeah, this is the hour that is given in seconds, perfect, 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 and this should be the season adjustment, so no big deal here. So why is it doing this is not clear to me. That's a strange one. The season is right. Seasonal adjustment, the PPV should be always positive. This is positive. And string PM is the value of the, yep. If this is negative, then the other is negative too. Correct, correct, correct. So this is right. But why this is happening, this is very strange. So let's go back to what we started with. Alright, so we have a 420, where we said 40 modules of 420 power are going to be at 1800 volts operational voltage. Okay? So the numbers are correct here. So if this power is, so if this power is correct and it should give the hump as we saw it earlier, this voltage here would be the desired maximum voltage, and this perturbed observed should give the proper V reference for the module. But the V reference here, VPV, this is the voltage of the photovoltaic. Yes, so when it is coming out, that's an interesting issue here that occurs. Why though? So you give the 50 initially and then you're allowed to give the voltage reference. And this is a control signal, okay? So you're checking whether the previous and the following voltage makes sense. Okay, okay. So that adjusts the voltage of the reference. So with a short delay, okay, maybe I should try the actual time delay for this just in case. It's super slow, but it doesn't matter. Let's do this here. Okay, transport delay, perturb observed. Okay, so you change the voltage here, give the value, and this is going to tell you if the previous power is increasing or decreasing. Yes. The steps don't affect us at all. Perfect. No, we don't care about the steps. So, yes. That is very strange. That is very strange. So when I'm adjusting the voltage here, maybe I could use like something like a saturation here to not go to negative values to make our lives easier. So with that, it's going to be adjusted. So let's do a discontinuity here with the saturation. So the saturation should be upper limit infinite, lower limit, let's put it 2. Okay, control rotate, alright, come here, let's see now. This thing, the voltage is very strange. Let's see if it passes the 5 seconds, which is always, okay, it passed it. Let's see the voltage, it goes again to negatives, which should not,